We are starting section 8.2, and it's an introduction to hypothesis testing. The first 3 or 4 pages is what I put in to try and make you kind of understand what was really happening. And then we'll start with the actual material that we'll be covering. So in another course, someone asked me, how do we tell if a coin is fair? So what are your ideas? How could you tell if a coin was fair? Not necessarily the right way, just how could you tell if the coin was fair?
So if it follows the probabilities, you basically have to run the test.
Okay, you have to run the test to see if it follows the probabilities. Be more specific, like.
So if it's 50% heads, 50% tails, reliably over a certain sample size.
So you want to flip it a lot of times and see if it's 50% heads, 50% tails. Okay, any other thoughts? That one seems fairly reasonable to me. So I do have a coin, okay? So let's say we wanted to flip it 10 times, just to not have to spend forever on it, okay? If the coin is fair, how many times would you expect to get heads out of our 10 times? 5. Okay, so let's flip this coin. We assume that it is fair, and we're going to see our results. Anyone here a really good coin flipper? Want to flip our coin? You want to do it for us? Pretty fun, right?
Yeah.
So 10 times, just yell it out for us, and we'll write it down.
Heads. Heads. Tails. Tails. Heads. Tails. Heads. 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 Tails.
Tails? I hope you guys are keeping track, because my things kept erasing everything I wrote, so I'm going to try and restart this. Did anyone keep track? Someone else is doing it. Okay, let me restart that really quick and see if maybe this time it will let me write and not erase everything. Okay, can you tell me what the sequence was? Head, head.
Head, tail. Head, tail. Head, 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 head.
Is that correct? Okay. Okay, so for this coin, we got 1, 2, 3, 4, 5, 6 heads. Okay, so how do you feel about that coin?
Pretty close for a small sample size.
It's pretty close for a small sample size, so that coin's probably pretty fair. Okay, so even if our coin is fair, are you going to get exactly 5 out of 10 heads every time? Okay. No, it's a random variable. We expect to see some variation. So now I'm going to ask you, how many heads do you think you can get in 10 tosses and still think the coin was fair? Okay, so you said at 6 heads you thought it was fair. Like, what is your range here for what makes a fair coin? Now, we don't have any mathematical reasoning yet, just someone like, what's kind of your gut feeling? How many heads could you get and still think this coin was fair?
Out of 10 tosses?
Mm-hmm, out of 10 tosses.
I think 6 is about the limit for me. But
Okay, well, let's see, are you going to include the 5? Let's start there.
yeah.
So you're going to include the 5, you're going to include the 6. If you include the 6, you should probably also include 4. Okay. How many people want to go to a 7? Okay. Only a few of you. Most of you, you want to say the 4 and 6. Okay. So we'll say 4, 5, and 6. And then, so that means then how many heads would you have to get to think that the coin was not fair? Okay. According to our 4, 5, and 6 to make it fair, we'd have to have 0, 1, 2, 3, and 7, 8, 9, and 10 would be our rule for if it is not fair. Okay, and again, why do we pick these numbers? This was just our gut feeling. No mathematical reasoning. Some of us even wanted to go higher than other people did. Okay, so it was pretty subjective so far. So what we're going to do when we do a hypothesis test is in advance we make up this rule. And we say, okay, well we'll believe that the coin is fair if we get 4 to 6 heads and 10 tosses. And we'll believe the coin is not fair if we get 0 to 3 or 7 to 10 heads. Now technically we should go through and try and find a more mathematical reason for our boundaries. Okay, but this is how you do a hypothesis test, is you decide, well, what will be my boundaries? And we make a rule. So we're going to flip an electronic coin using this coin tossing applet, and for each coin we don't know if it's fair or not, and we have to use our rule to decide if we think it's fair. Now remember, we are dealing with probability, so even though getting 10 heads out of 10 tosses would be really unlikely on a fair coin, it's still possible. I mean, even if it's only a 1 in a 10,000 chance, it could still happen. So our decision might not always be right because you might get these very unlikely events. So we're going to fill out this table as we go. Okay. So we can flip the coin 10 times. It tells us, okay, that we got 2 heads. Okay, so 2 heads, what is our rule? So ignore everything else, just look at 2 heads. Do you think the coin is fair? According to our rule, no. So no says the hypothesis, the coin is fair. We don't think that's true, so we're going to reject it and see if we're right. We were right. The coin was not fair. The probability of heads was actually only 0.28. So we got 2 heads, our decision, not fair. The truth was that it was not fair. And was our decision correct? Yes. Okay, back to the applet. Let's get a new coin and flip it 10 times. This time we got 8 heads. Okay, according to our rule, what are we going to decide? Not fair. Let's check it. So we think the coin is not fair, so we will reject that hypothesis. And in fact, that coin was fair. So 8 heads, our decision is not fair. The truth is that it actually was fair, so were we correct? No. New coin, 10 times. Okay, we have 1 head. According to our rule, what is our decision? Not fair. And we were correct, the coin was not fair. The probability of heads was only 6%. So, 1 head, not fair. And the truth was that it was not fair. So our decision is correct. New coin, flip it 10 times. This time we got 2 heads again. And our decision would have to be that it is not fair, so I'll reject the hypothesis that it is fair. And we were correct. Last one. Okay, we got 6 heads. What is our decision? What is our decision?
Yes.
We think it is fair. And it was fair. We were correct. So that is kind of a basic test. We made a rule, we looked at our data, and we tried to decide, okay, according to our data, what decision should we make? So let's label some of our intuitive work with some statistical terms. Okay. So the first thing is the null hypothesis. This is the status quo, or the statement being tested. So in our case, we were testing to see if the coin was fair. Now, your alternative hypothesis is the opposite of the null hypothesis. So the opposite of the coin is fair is that the coin is not fair. Now, usually what you're trying to prove or show is usually actually going to be your alternative hypothesis, because you set up the status quo as the null hypothesis, like this headache medicine doesn't work. You set that up as the null hypothesis, and then you try and prove that it's wrong and that you have evidence for the alternative hypothesis that the headache medicine does work. Now, your test statistic is a value computed from your sample data. Okay, and there's many different tests, many different test statistics. In this case, what value did we look at for each data set to try and decide if the coin is fair or not? The number of heads. We also have what's called the acceptance region. That's the set of values of our test statistic that will convince us to believe the null hypothesis. So in our situation, the null hypothesis was that the coin was fair. And we said we would believe that the coin was fair if we got 4 to 6 heads. So that was our acceptance region. We decided in advance when we would decide if this coin was fair. And the rejection region is the set of values for our test statistic that will convince us that the null hypothesis is false, which was 0 to 3 and 7 through 10. Did anyone need one more copy of this? I have my copy. Yeah. So were we right every time when we use this hypothesis testing? Okay. No, and so it is possible to make errors, and what we're going to try and do through our statistics is try and make those errors as small as possible. Oh, that's where all my writing went that disappeared. I've never had to do that before. Really strange. Okay, so how did we pick our rule to decide if the coin was fair?
Yeah.
Our gut feeling, instinct, absolutely no mathematical reasoning, right? Besides the fact that we picked numbers that seemed kind of close to our expected value. Okay. So, how do you feel about that as a way to make decisions? If you were running a multi-million-dollar company, well, I guess sometimes they actually do trust their instincts quite a bit, but you might want a more mathematical way to pick your numbers. Okay. Also, if you have to convince someone else, you might need to have a mathematical reasoning so that they believe you as well. So, can you think of any mathematical or statistical way to approach making a decision rule? Okay, or picking our acceptance and rejection regions.
You say you want it within a certain standard error of the mean.
Okay, we can say we want it within a certain standard error of the mean. What kind of standard error would you pick?
I guess it depends on the sample size.
Okay, it depends on the sample size. Well, think about it this way. So the empirical rule tells us 95% of our observations should be within plus or minus 2 standard deviations of our estimate. And the standard error is just how many standard deviations of our estimate. So if we wanted to be 95% accurate, we could say we want to be within plus or minus 2 standard errors. Okay? And that is essentially the way that we're going to do this problem. We're going to say it slightly differently, but that is what we're going to be doing. So for this specific example, it's not necessarily going to be normal distribution, so we're not going to use the empirical rule. But we can look at the probabilities for each value of heads. Okay. Now, the number of heads that we get in 10 coin tosses is a binomial distribution. And if we assume that the coin is fair, then our probability of getting a heads is 0.5, and n equals 10 for our binomial distribution. Now, it is very important on this that we have to assume the coin is fair, okay, because that was our null hypothesis. So we assume that the null hypothesis is true, and then we find probabilities associated with that. Okay. So if we assume it's true, then the probability that we get 0 heads is 0.0010. So I probably think that the coin is not fair if I get 0 heads. At 1 head, the probability is 0.0098. That still seems pretty unlikely. For 2 heads, the probability is 0.0439. So you have about a 5% chance, 4 or 5% chance. That's not too unlikely. So if you had a fair coin, you might still get 2 heads occasionally. 3 heads is 11%. That's pretty likely. I definitely would believe it was fair, or it could be fair if I got 3 heads. 4 heads was 0.2. Like 7 heads is 11% again. 9 heads is 0.098. 10.010. Okay, and here is the lovely graph. So with our first decision rule, okay, what is the probability that we'll decide that the coin is not fair in error? So the coin really is fair. So using these probabilities, what was the probability that we decided it was not fair? Okay, so we said not fair if 0 to 3 heads and 7 through 10. Okay. So if the coin is fair, okay, then the probability of getting x equals 0, 1, 2, 3, 7, 8, 9, or 10 is going to be what? Okay, how am I going to find this probability?
The sum of all those.
Okay, just the sum of all those. So that's 0, 1, 2, 3, 7, 8, 9, 10. 0.001 plus 0.0098 plus 0.0439 plus 0.1172 plus 0.1172 plus 0.0439 plus 0.0098 plus 0.001. I got 0.3438. Anyone else?
I got 3.3437 with the complement rule, so.
I had to times it by 2. Oh, the rounding's probably off because I'm not everything for decimal places. That's why. So when we look at this, this means if our coin really was fair, the probability that we decided it was not fair in error was about 34%. Let's go back up and look at our table really quick. So the times, there was one time that it was fair and we decided it was not fair. And that was when we had the 8 heads. Okay. But our probability of making that kind of mistake was 34%. How do you feel about that 34%? Probability of making that type of mistake. That seems pretty high, right? Okay. We know, because we've talked about this a lot, if I want to make this error smaller, I could just, what's the one thing that I could easily do that would automatically make all of my errors and everything more accurate? All of my errors smaller. Increase the sample size. Okay. But since we're still on our 10 coin tosses, let's pick a different decision rule that will ensure that the probability that I make an error and decide that a fair coin is biased is less than 5%. So how could I change those probabilities? What would my new rule have to be so that this probability is less than 5%?
have to assume that a fair coin will be from 2 to 8.
Okay, so you said a fair coin has to be from 2 to 8. Let's check that. So that means it would be not fair for 0, 1, 9, and 10, correct? So let's add those probabilities together. How could you tell that these were the only ones that I can include without actually adding them together?
They're really small.
They're really small, and specifically the next value is
It's almost 5%.
it's almost 5% by itself. Okay. So right now I'm at 0.0216. So the probability of that error would only be 2%. Okay, are there any other values that I can add in without making it over 5%? Okay. Nope, that's the most I can do. You might have noticed as I went through that I did pick, if I picked a 0, I put in the 10. If I picked a 1, I put in the 9. Like, why did I do that?
Because of the symmetry.
Because of the symmetry, and each one is equally likely. Yep. Now, is that the only type of error that I could get? Okay, of deciding if fair coin is biased in error. What's the other type of error that I could have? Or let's look back up at our table from when we were incorrect. Oh, that was the only time we messed up. Never mind. Okay. Would it be possible to have a biased coin and accidentally say that it was fair? Okay. That would be another possible type of error. But as far as finding that probability, it gets more difficult because the probability for each one of those is you would have to know what the probability for the biased coin is to find the probability of that type of error. And there are lots of different probabilities that we could have for biased coins. But for this probability that we just found, this probability is alpha. Okay? It is the probability of a type 1 error. So the probability of a type 1 error equals alpha. Okay. So a type 1 error is when we reject a true null hypothesis. So that means we decide a true null hypothesis, so the coin is fair and we think it is biased. So that's a type 1 error. So what we did is we controlled the probability of our type 1 error. We said we want the probability of our type 1 error to be less than 5%. And we made our new decision rule that actually got our probability of a type 1 error down to about 2%. And then, so that's a type 1 error. The other type of error is a type 2 error, and that happens when you fail to reject a false null hypothesis. So a false null hypothesis would mean the coin is biased, but we think, what would be the error here? We think it is fair. So notice, two different types of errors. They are going to have different probabilities. Then we also have what's called a level of significance. So the significance level is also going to be equal to alpha. And what this does is our evidence is considered to be strong enough to reject the null hypothesis if the data in our sample would only happen 100 times alpha percent of the time, or less when the null hypothesis is true. So what this means for us is if the null hypothesis is true, so this means if our coin, is fair, we will only get evidence to make us decide it is not fair. Let's see, 2.16% of the time. So basically, it's just another way to reword the probability of a type 1 error. Okay. So if our coin really is fair, we're only going to get these extreme test values, or evidence that makes us think it is not fair, only 2% of the time. That seems pretty good. I can live with that kind of error, I think. Okay. We're going to usually choose a significance level of alpha equals 0.05, alpha equals 0.01, or alpha equals 0.10 are the three most common. And we will talk about these in more detail later, but 0.10, okay, that means you have a 10% chance of making an error. Usually the only people that use such a big probability of an error is the social sciences. Okay. 0.05 is accepted by the Supreme Court. So if it's good enough for them, it's probably good enough for you. And usually 0.01 is if you're dealing more in the sciences, where if you're dealing like with new medications, or maybe trying to get something ready for a space flight, something where it really makes a big difference. Okay, and you really need to be accurate. So just keep that in mind, like depending on what you're working on, you might choose a different level of significance, or the probability of your type 1 error. Okay, but our default is 0.05. Now, because your textbook was written for engineers and scientists, they prefer, I think, the 0.01. So they say anything smaller than 0.01 is you have really strong evidence and you're good. Bigger than 0.10, they say, oh, we don't believe it. And they say anything in the middle is like inconclusive. But really, I'd rather go with what's commonly accepted overall in statistics, which is our default is 0.05. Partly because that is recognized by the Supreme Court. So let's try another example, which is, again, just kind of reinforcing these concepts before we actually learn how to do a z-test. Okay. Suppose we have a 6-sided die, and we want to know if it is fair. Okay, so same concept. If the die is fair, how many times would you expect to get a 4 if we roll it 10 times? How would you figure that out? 1/6 times 10. I don't know what that is. 1.66. 6. Okay. Now, if our die is fair, because all the probabilities we find are always based on the assumption that our die is fair, if the die is fair, then x, which equals the number of 4s rolled on the die, because it makes sense to count the number of 4s. Now, could I have counted the number of 5s or number of 6s? Yeah, I just had to pick something, so we're going to count the number of 4s. It has a binomial distribution with n equals 10 and p equals 1/6. Now, when you look at this distribution, is it symmetric anymore? Okay, no. And if you think about it, if I only expect to get 1.666 4s, well, like 0 4s is pretty close to that, so 0 probably make me still believe it, and so it's not going to be the symmetric thing anymore. So here are our probabilities. Like we have a 16% chance of rolling a 0, 32% chance of rolling a 1, 5% chance of rolling a 4, 1% chance of rolling a 5, etc. Okay, if the die is fair. So we want to use a significance level of alpha equals 0.05. So it's always 0.05 or less. So we want to make this probability 0.05 or less, the probability of making a type 1 error. So what would be your null hypothesis in this situation? Okay. Just in words, null hypothesis, I'm looking for is the dice fair or is the dice not fair? What would be the null hypothesis? The dice is fair. That would be kind of our status quo, or the thing that we're going to test. And the alternative then would be that the die is not fair. What is our test statistic? What is the thing that we're counting when we roll a dice to try and decide if it's fair or not? Number of 4s. So let's make our decision rule for what will be our acceptance regions and rejection regions for this. Okay, so what I need to do, remember, is I want to make sure that the probability that I reject this fair coin, that I decide it's not fair, is less than 5%. Okay, so what would you do to try and figure this out? How did we do it last time? Well, where would you start deciding the die is not fair? Are you going to start deciding the coin is not, or the die is not fair at 0 fours? Okay. No, I need to start at the other end and add them up until I get to 5%. So I can probably include the 0, 0, 0, that one, probably that one, maybe this one, but I need to add them up to be sure. Am I going to include the 4 fours? No. So let's try and add it up and see if it works. So for my rejection region, or for my decision rule, let's find the probability that x equals 10, 9, 8, 7, 6, or 5. Okay. So what are those probabilities if I add them up? Or if you use the complement rule, so I'm going to go ahead and try that. Okay, so I got 0.0155. Okay, anyone else? Okay, so is this still less than my 5%? Yes. Are there any other probabilities that I could add in without making it over 5%? Okay, no. So that's where I have to stop. So I'm going to say I will decide it is not fair if x equals 5 through 10. So if the number of fours is between 5 to 10, and then that means that I must think that it is fair if 0 to 4 fours. So that's how you go through and you make a decision rule. Any questions so far?
Well, I have a question.
Yes.
Why on the last one did you look at the lower end and then the upper end, and this one we only look at the upper end?
Okay, because on the last one our distribution was symmetric, so getting like 0 heads was just as likely as getting 10 heads. But when you look at this, our distribution isn't symmetric, it's very right skewed, and if you try and look at the lower ends, the probability of getting 0 is already at 16%, which is fairly likely on a fair coin. And so if I get 0 fours, I'm still going to believe that this is fair, and that probability was already bigger than 5%, so I couldn't include it in. So I would say in practice you would always just start at the ends and work your way in, but when I try and start at my lower end, it's already too big to include. So we're going to use another applet. Okay. So different dice, 10 times each. So I'm going to ask you what the test statistic was, the number of fours, our decision. Okay, and then we're going to talk about whether we fail to reject or reject the null hypothesis. Okay, so what do you think that means? When would I reject a null hypothesis? Okay. So remember, our null hypothesis is the coin is fair. So if I reject the null hypothesis, that means that I decide the coin is not fair. And fail to reject means that I don't reject it, so I still believe the coin is fair. Okay. We'll look at the truth, if we made an error, and if we made an error, what type of error. And if we're lucky, we'll make both types of errors so that we can compare them. So again, there's more than we need on here. But if we roll the dice 10 times, remember we're only counting the 4, so how many 4s did we get? 1. So coming back, we rolled 1, 1. So according to our decision, are we going to accept or reject? Or do you believe that this is fair or not fair? Okay. We got 1, so we believe it is fair. Okay. So our null hypothesis was that it was fair, so we should fail to reject it. Let's see if we were correct. Go look at the truth. Okay, so we accept the hypothesis that the die is fair, and we were actually wrong. The die was not fair. So, did we make an error? Yes, and since we made an error, what type of error is it? So look back up. Is it a type 1 or type 2 error? 2. Why is it type 2?
It wasn't fair and we called it fair.
It wasn't fair and we called it fair. Let's try again. So we roll it 10 times. Look at the 4s. We got 0 4s. Okay, so our decision is that the coin or die is fair. Okay, and so our null hypothesis of the coin is fair. So do I want to accept it, which is also another way to say fail to reject, or do I want to reject that null hypothesis? Not reject it. So we'll say fail to reject. Okay. Let's go figure out what the truth is. So we accepted the hypothesis, and no, the die is not fair. We are not doing very well, are we? Okay, so we made an error, and once again this would be type 2. Okay. Looks like this time we got 3 4s. So 3 4s, what is our decision? The coin or die is, let's see, 3 still falls within my acceptance, so fair. I will fail to reject, and hopefully we got this one right. No, we're still doing it. So the truth is not fair. Yes, and once again it is a type 2 error. Okay. Let's see, we have 0 4s, which means we believe it is fair. Fail to reject. Cross your fingers. We were right. The coin is fair. Did we make an error? No. So, no error. We're good. Let's see. This time I have 1 4. Okay. So what are you going to decide for 1 4? Fair. And we will accept our null hypothesis that the die is fair. And the die was not fair. So 1, we thought it was fair. We failed to reject. And it was not fair. Okay. So we made an error. What type?
2.
Type 2. I'm going to go through a couple coins and see if I can get some high values of our 4s, just so we can practice with that. There you go. Last time I did this, we couldn't figure it out. Let's try another one with 3. So this time we got 3 4s, which means we think it is fair, and we will fail to reject. And we were right, the die was fair. So we didn't make an error. they need to change their probability generator. So I really want to get a value like 6 or something so we can try that out. Oh, look, we got a 4. Okay, so we got 4 4s, which means we think it is fair, and we will fail to reject. And we were right, the coin was fair. So no error was made. So we weren't able to find any type 1 errors here, but that's okay. It's probably because we made the probability of a type 1 error smaller than 2%, so we weren't really expecting to find one. Okay, now in this situation, all that we've reported so far is if we failed to reject or rejected the null hypothesis. Okay? But we don't reject the null hypothesis if we roll 2 4s, but we also don't reject the null hypothesis if we roll 4 4s. Okay? Now looking previously up further on your page, what is the probability of rolling 2 4s on a fair die? Okay, what was the probability of rolling 2 4s on a fair die? 29%. What is the probability of rolling 4 4s on a fair die? Okay, so let me ask you now, what would make you more likely to believe that this die was fair if you rolled 2 4s or 4 4s? 2, right? Like, assuming you don't have the computer to check afterwards to know if your die was fair, if this was really out in real life and you want to know if this die was fair, I'd feel a lot more confident if I'd rolled 2 4s. And instinctively, the reason that you feel that it's more likely is because the probability of it under the null hypothesis was higher.
So because we used a significance level of 5%, does that mean we should be like correct on our guesses 95% of the time? Is that what that's saying?
That means as far as making a type 1 error goes. Okay, so we're only going to make a type 1 error 5% of the time. But we can also make a type 2 error, and that error could be quite a bit bigger. And that error is difficult to figure out because the probability of a type 2 error, that's the probability of deciding a biased coin is fair. And how do you decide the probability of deciding that a biased coin is fair? You would have to know the probability of the biased coin, or in this case, the biased die. And in practice, it's kind of hard to know the probability of a biased die. And what are all the options for it? Well, a biased die could be like 1%, probably 1% of 4s. It could be 2% of 4s, 3% of 4s, 5% are 4s, 50% are 4s, 100% are 4s. Those are all possible alternative values for the probability of rolling 4s. Okay, and so there's many different ways that I could have a biased coin and accidentally decide that it is fair. Now, how can I just make the probability of all of my errors smaller? Increase your sample size. Okay. At only 10 tosses, we're really probably going to keep our probability of a type 2 error fairly high. So the next thing we introduce is called a p-value. So a p-value is the probability of observing our test statistic or something more extreme if our null hypothesis is true. Okay. Now, more extreme to us means that the data set would give us even more evidence against the null hypothesis. So anytime we say extreme, means it's evidence against the null hypothesis. Okay. So for example, if we rolled 5 4s, the p-value is the probability that we would roll 5 or more 4s with a fair die. Okay. So it's always going in the direction against your null hypothesis or towards your alternative hypothesis. The reason we report our p-value is so that people can see how strong our evidence is and not just our conclusion. So for each of the dice above, we want to find our p-values. Okay, so can someone flip back to the previous page and just read off for me the test statistics? So how many 4s we got on each dice?
1, 0, 3, 0, 1, 3, 4.
Okay, so those were our test statistics. So for die 1, the p-value is going to be the probability of getting x greater than or equal to 1. Okay, because remember, we're always going in the direction that gives us more evidence against our null hypothesis, which would be 1 and greater. So p-value, so I made a nice table for you. So the probability that x is greater than or equal to 1 is 0.8386. Okay, so what this means is if my null hypothesis is true, then the probability of seeing 1 or more 4s is 83%. And that makes sense because we expected to get 1 4s. There should be a pretty high probability of getting 1 or more 4s. Okay, for the 0, that's the probability that x is greater than or equal to 0, which should be 1. Okay, so if our die is fair, the probability that we get 0 or more 4s is 100%. For the 3, probability that x is greater than or equal to 3 is 0.2249. So if the die is fair, the probability we get 3 or more 4s is 22%. 22%, that could happen. I could believe that this happened. So I'm going to still say that the die could be fair at a 22% probability. Let's see, we've already done the 0, we've already done a 1, we've already done a 3. Let's do the probability that x is greater than or equal to 4. So that is 0.0649. So the probability that we get 4 or more 4s is 6.5%. Not super likely, but I could still believe that it could happen. So I'm still going to have to go with my die could be fair. So what was our p-value if we rolled 4 4s? The probability that x was greater than or equal to 4 was 0.0649. What is your p-value if we rolled 5 4s, which we never did, but the probability that x could be greater than or equal to 5 is 0.0155. Okay. Now, do you remember what our significance level was? They told me that my probability of a type 1 error had to be what, or less? It was alpha equals 0.05 or 5%. Okay. Do you remember what your decision rule was? We said we will believe it is fair, so we accept the null hypothesis if we get 0 to 4 4s. And we decided that we would decide it was biased or not fair, so reject if we got 5 to 10 4s. Now, do you notice anything there? Okay, so our decision rule is we broke it between 4 and 5. Do you notice anything about the p-values for 4 and 5 compared to our significance level? One is above the 0.05, one is below. So, in statistics, or as we do our hypothesis testing, if the p-value is bigger than alpha, okay, so bigger than alpha, so like 0.0649 is bigger than 0.05, then we will accept or fail to reject. Okay, two different ways to say it, the null hypothesis. Which means then that if my p-value is smaller than alpha, we will reject the null hypothesis. So any questions on this page on like our p-values? So let's go ahead and start. So what we're going to do is summarize what we've learned. Okay, so it probably feels like we're going over this like over and over again. It's because this is going to lay the foundation for the rest of our semester. Okay, and it's important that you understand these base concepts. Okay. So once again, we have our null hypothesis. We're going to use the symbol H with a little 0. And it's a statement that we're testing. It's usually the status quo. And we assess the strength of our evidence against our null hypothesis. Now, one of the things that we do here is our null hypothesis is not rejected unless there's convincing evidence that it is false. Okay? So because it's our status quo, we're going to believe that it's true unless we have very strong evidence against it. Okay? And you can think of your null hypothesis as what you want to disprove. Okay. The alternative hypothesis with H with the A is the statement that we will accept if we decide the null hypothesis is false. Sometimes it's called the research hypothesis, and it's usually actually what you want to prove or what you really actually are interested in. So the hypotheses refer to population parameters. So we just wrote it as the coin is fair, but I could have said, well, if the coin is fair, then the population probability of getting heads was 0.5. So I could have written it in terms of a parameter. Okay, and there's different kinds of alternative hypotheses. So for example, let's say we want to test the null hypothesis that a population mean is equal to 3. There's 3 different ways that you could write this, or 3 different possibilities. So you can have the alternative hypothesis that your population mean or average is greater than 3. That might be what you're interested in. Or you might be interested in, is my population mean less than 3? Or you might just want to know, is my population mean different from 3? Any one of those could be viable alternatives. Okay? And it all depends on what you're interested in. But you need to pick your alternative hypothesis before you start looking at your data to be ethical. Okay? So for something like, if I want to see if this diet pill helps me lose weight, then I would put weight gain. So I put my weight loss as a positive number. So I want to make sure I lose at least this much. Okay? I don't want to look at my data and then change my alternative hypothesis to make it fit my data. So we're supposed to pick our hypotheses before we look at our data. We also pick our significance level before we look at our data. Now our test statistic, remember, is a value that we compute from our data to find evidence for or against the null hypothesis. We use test statistics because we don't just want to report all of our raw data to our boss, so we need to boil it down a little bit into a test statistic that we can evaluate. For most hypothesis tests, the test is going to be based on a statistic that we use to estimate our unknown population parameter. So if you want to estimate your population mean, what could be a sample statistic that you could use to estimate that? Your sample mean. Or if you want to estimate your population proportion, you would estimate it with your sample proportion. And your test statistic will be based on that. Okay. Now this isn't true for all tests, like we just did tests without using this, but this is most of our mainstream tests. If the null hypothesis is true, then you would expect your estimate to be close to your true value. So if my null hypothesis is true, then I would expect to get a sample mean close to my population mean. So if we get an now let's talk about our sample means and population means. In this situation, for this example, we had a population mean of 3. So for my null hypothesis, I believe that my population mean is 3. If your null hypothesis is true, what kind of sample means would you expect to get? Your sample mean should be close to 3. The closer it is to 3, the more likely you will be to believe that your population mean really is 3. So if I get a sample mean of like 2 or a sample mean of 4, that might be fairly close, depending on my standard error. What if I got a sample mean of 100? How do you feel about your population mean being 3? Probably not very good, right? So the closer your the closer your estimate is to your population parameter or your hypothesized value, the more you believe the null hypothesis is true. The further away it gets, the more you will believe it is not true. Okay. Now, to see how far it really is, you need some way to standardize it or to look at the standard error. So what we're going to do is we'll do your estimate minus your hypothesized value divided by your standard error or the standard deviation of your estimate. And that's just a way to scale how far is it from your hypothesized value. Okay. Once again, your p-value is the probability of getting an outcome as extreme or more extreme than the actual observed outcome if your null hypothesis is true. Remember, extreme means far away from what you would expect if the null hypothesis were true. So more and more evidence against the null hypothesis. The smaller the p-value, the stronger the evidence against your null hypothesis, and the stronger the evidence for your alternative hypothesis. Now, statistical significance is if your p-value is as small or smaller than alpha, so a small p-value, we say that our data is statistically significant at that level of significance. Remember, your significance level is the amount of evidence against the null hypothesis that you require to reject the null hypothesis. So, for example, if you choose alpha equals 0.05, then you're requiring that our data gives evidence against the null hypothesis so strong that it would only happen 5% of the time if it's actually true. Or in other words, the probability of making a type 1 error is only 5%. Okay? Again, common levels are 0.10, 0.05, and 0.01. By convention, so this just means the people that named it, they got to make up the words for it. They say if alpha is 0.05, then we're requiring strong evidence to reject the null hypothesis. And if alpha is 0.01, then we are requiring very strong evidence to reject the null hypothesis. Now keep in mind, this is, you set in advance how much evidence you will require. When you find your p-value, that tells you how much evidence you actually found. Because you could find more evidence than you require or less evidence than you require. Okay. So let's see how this actually comes into play. Actually try an example. So the first test that we'll use is a one-sample z-test for population mean. And in this situation, you have to know the population standard deviation. So you'll use this test if you want to know the value of the population mean mu, but for some reason you already know the population standard deviation. Now you might imagine, just like in the confidence intervals, this is probably never going to happen in real life, or at least very rarely. But again, it's the easiest one to teach, so we'll start with this. The assumptions to use this test is that our population is normally distributed or the sample size is large, at least 30. That shouldn't surprise you because that was our requirements to use confidence intervals, that was our requirements to find probabilities using the normal distribution. Okay. Our null hypothesis is that mu equals some hypothesized value. So this could be like, we think that the population mean is 3, or we think that our population mean is 250, etc. Our test statistic, okay? Remember, we said our estimate of the population mean will be our sample mean. So it's x bar minus my hypothesized mean. So if I think my mean is 3, then I will minus it 3. And then we need to divide by the standard deviation of x bar, which is sigma over the square root of n. Okay. And then as far as p-values, what I want you to remember is that the p-value will always be the area in the tail or tails. Okay, so you could memorize the formulas that the book has, and when I went through and I took Statistics 3000, I memorized all the formulas, and I had my cheat sheet for every test, and I'd have to go look at it every time, and then I finally realized it's just the area in the tails. I can just draw pictures. I don't have to memorize complicated looking formulas. Okay, so if my alternative hypothesis is that I think that my mean is greater than hypothesized value. So let's say once again, for an example, let's say that I want to see if my mean is 3. I think my population mean might be 3. Then my alternative hypothesis, the first one that I could choose, is that maybe my mean is greater than 3. Okay? So if you think that maybe your mean is greater than 3, then the higher and higher sample means you get, the further and further you go out, you might have more and more evidence against the alternative hypothesis, or sorry, against the null hypothesis. So because it's a greater than, we will be looking for the area in the right tail. Okay, so notice you have a little z-value there, and we're just looking for the area under the standard normal curve to the right of our z-value. Remember, we'll find the z-value by using our standardization formula. Okay. If I want the alternative hypothesis, that maybe my mean is less than 3, then I would look at the area in the left tail. And if I think that my mean is not equal to 3, okay, well, if this is my positive z-value, and this is my negative z-value, I would just want the area in both tails. Now, because it is symmetric, if you find the area in one tail, what's there in the other tail? The same thing, and you just have to times it by 2. Now, to get a correct formula, we do write the absolute value of z, because we don't know if the z-value you get is going to be negative or positive to start with. Okay, but just draw your picture, find the area in both tails, and add them together or times by 2. Now, we do have steps of hypothesis testing. Different books, different people will condense these. Sometimes I've given it to my students in 5 steps, sometimes I make like 8 steps, but it all boils down to the same thing. And the order you do some of these in can change as well. So, find your level of significance, or specify your level of significance. Remember, that's your probability of making a type 1 error. So you get to decide in advance how small you want to make that. Okay? You need to check your assumptions. So, am I even allowed to do this test? In this case, we need to check and see if our population is normal or we have a large sample size, because otherwise there's no point in continuing. You need to have your null and alternative hypotheses. You need to collect your sample data and compute the value of your test statistic. Calculate the p-value, and you reject the null hypothesis if your p-value is less than alpha. And because there's no point in doing this if you can't relate it to the real world, you should interpret your results and assess their practical significance. So, what are you actually going to tell your boss? Now, the first 3 steps, the order doesn't matter. You just need to make sure that you do them all eventually. The last 4 steps, you kind of do need to do them in order, because you can't find your p-value until you find your test statistic. And I realize we've gone through a lot of information, so let's just try a problem, because as always, it makes more sense if you just try it. So for example 4, a trash bags company's current bags have a breaking strength of up to 50 pounds. They think that their new bag will be stronger. From past experience, they believe that the standard deviation of all their breaking strengths is 1.65 pounds. What does that 1.65 pounds sound like to you? That's the standard deviation of a population or a sample? Population, where they say all the breaking strengths, that to me sounds like it is their population. So I'm going to say sigma equals 1.65. A company randomly selects a sample of 40 new trash bags. So that means n equals 40. Okay, and finds that the sample mean is x bar equals 50.575. We want to conduct a hypothesis test at significance level alpha equals 0.05. Okay. And let's see, what else have I not looked at? Their current bags have a breaking strength of up to 50 pounds, and they think their new bag will be stronger. So it sounds to me like they want to show that, let's see, well, they could look at the mean, the population mean. Do you think they want to show that the population mean is greater than 50, less than 50, not equal to 50? They want to show that it is greater than. So they want to show that my population mean is greater than 50. Now, it doesn't necessarily say in there anywhere that they want to look at the population mean, but they want to know if their bags are stronger, okay, and so that would be a good way to look at it, is look at the average strengths. let's see. So we need to go through our hypothesis test. One of the first things we need to do is our level of significance. They already told you your level of significance, so we're good there. I need to check my assumptions. So we need to have a normal population or a sample size of at least 30. Okay, are one or both of those fulfilled here? Okay. We have a sample size of at least 30, so we can use this test. What would my null hypothesis be? What would be the status quo?
It's greater than 50.
Okay. Well, they want to show that it's greater than 50. Their current bags have a breaking strength of 50, so the status quo, if nothing changed, would be that it is still 50. So it kind of takes a while to get used to the fact that what you want to show is your alternative hypothesis, and the status quo, or nothing interesting, is your null hypothesis. Also, until I tell you otherwise, all of your null hypotheses for this class are always going to be in equals. Okay, so like when you looked at this test, the null hypothesis was in equals. I didn't give you any other options. What's next? Compute the test statistic. We don't have to collect the data, they've already done that for us, but we need to collect our test, or find our test statistic. So z equals x bar minus my hypothesized value for the mean over sigma over the square root of n. Okay, this formula should look really familiar. When have you seen a formula like this? When you found probabilities for the sample means, the only thing that's different is we have that little O there on our mu to remind ourselves that it is our hypothesized value. We don't know the true value, it's our best guess. Okay, so x bar, 50.575, minus my population mean, my best guess for my population mean, which is my 50, or just your null hypothesis mean. Standard deviation is 1.65 over the square root of 40. .20. Anyone else? So that was my test statistic. Now let's find my p-value. So I would just start, and I draw my picture. I say, well, what was my test statistic? 2.2. And then I have to decide which direction am I interested in shading. Okay. So my alternative hypothesis was that my mean is greater than 50, so evidence for that means I need big values. I need to shade to the right. So I need to find the probability that z is greater than 2.20. So I'm going to have to use the complement rule, and I pull up my standard normal table. For 2.20, that puts me at 0.9861, but that was the area to the left, so I needed to do 1 minus that. So my p-value is 0.0139. Now it is important that you interpret your p-value correctly. So I told you that confidence intervals, interpreting them incorrectly was one of the most common mistakes. The other one is p-values. Okay. Because who wants to look at that and say that that's the probability that the null hypothesis is true? Okay. So that's probably the most common way that people try and say that, because they want to try and simplify as much as possible, but you cannot simplify the definition of the p-value. This 1% means that you have a 1% probability of seeing your sample mean of 50.575 or bigger if the population mean really is 50. So if the population mean really is 50, then the probability of getting a sample mean of 50.575 or bigger is only 1%. Okay, so how does that make you feel about having a population mean of 50? Not very good, right? And in fact, is that a big or a small p-value? Okay, so is your p-value bigger or smaller than alpha? Okay, so my p-value of 0.0139 is smaller than alpha equals 0.05. Okay. So anytime I have a small p-value, I will reject the null hypothesis. Now at this point, you've done a very nice math problem. But what are you going to go tell your boss? If you just tell him I reject the null hypothesis, that's probably not going to mean very much if he hasn't taken statistics. So we need to write a little bit. Okay? So we could say something like, we found, okay, and I haven't quite told you yet how much evidence, so I'm just going to say strong, and then I'll tell you why soon. So we found strong evidence, okay, that let's see, so what did we find strong evidence for? So we rejected the null hypothesis, which means that we no longer believe that this is true. What do we believe is true now? That mu is greater than 50. So what happens is we found strong evidence that the mean breaking strength of all the bags, since it's the population mean, is greater than 50. So because we reject the null hypothesis, now we have very strong evidence for the alternative hypothesis, which was that my mean was greater than 50. How much bigger do you think it is than 50? We still don't know exactly how big my population mean is, right? I have strong evidence that it's bigger than 50, but I don't know exactly how big. But what's your best estimate for how big your population mean is? And what was your sample mean? 50.575. So at the moment, that's my best estimate for how big my population mean really is. Okay. So I found strong evidence that my population mean is greater than 50, but still my best guess for what it is 50.575. Now let me ask you, if you were going to go out and buy a trash bag, do you really care if your breaking strength is 50 pounds or 50.5 pounds? It's probably not going to make a difference to you whether or not you can put in that one more can. Okay. And so even though, again, you're sure that it is greater than 50, it's really not that much bigger than 50 to make a practical difference. So even though we know that it was statistically significant because we got a small p-value, that doesn't mean that it is practically significant. So practically significant means it makes a difference to us in real life. Okay. So keep in mind, sometimes when they say, we're very sure that it is bigger than 50, you might want to ask them, how much bigger is it than 50? Okay, so we've done a whole problem. So any questions on how you do this entire problem? How we do a hypothesis test?
I have a question. So how would it have changed if we set up our was it our alternative hypothesis?
Mm-hmm.
How does that change does it change how we find Z?
It will change based on what your alternative hypothesis is. If this is a less than, not equal to, or greater than, the only thing it changes is how you find your p-value. So for a greater than, I shade the right tail. For a less than, it would be like the left tail, and a not equal to would be both tails. So I think my next example should be something different, so you can see an example of a different alternative. But the only thing it changes is how you find your p-value. And so any other questions before we go on to the next one? Okay. So this should help answer your question. So we want to see if a new billing system can reduce the mean bill payment time to less than 19.5 days. So to me, that means that we want to show that the mean bill payment time is less than 19.5. So we want to show that our mean is less than 19.5. Okay, so we have that. We know that the population standard deviation is 4.2. We took a sample of 65 invoices. That sounds like a sample size to me. See what I meant when I say you really need to memorize these symbols? And we found a sample mean of x bar equals 18.1077. Okay, and what should you report to your boss? Okay, so he wants to see if the mean bill payment time is less than 19.5 days. Now you will notice that the first thing I do whenever I'm doing confidence intervals, hypothesis tests, or anything is I read through the problem statement and I try and write everything in the symbols. So then I know what to plug into formulas, and I even know like what formulas I need. So like when I look at this, I see a population standard deviation, so I know I need to use a z-test. So my first step is I need a significance level. Did they tell me a significance level? They didn't. Okay, so I get to pick one. I could pick like 0.01, 0.05, or 0.1. By default, we'll usually go with 0.05. I'm going to choose 0.01 here just to give you a little more practice. So I choose alpha equals 0.01. What else do I need to do or check? Okay, so normal or n of at least 30. Okay, which one is satisfied here? Large sample size. Okay, so we can do the test. Let's see, I need my hypotheses. Let's see. So your null hypothesis, remember we said it's always going to be the equals, and then the alternative is what you want to show. So I want to show that my mean is less than 19.5. So what would my null hypothesis have to be? mu equals 19.5. So status quo would be that it is 19.5, and I want to show that it is less than 19.5. So what's my next step? I need a test statistic. So x bar minus my hypothesized mean over sigma over the square root of n. Let's see, so that, and we just plug everything in. So 18.1077 minus my mean for my null hypothesis, which is 19.5, over 4.2 over the square root of n. So negative 2.67. So now I need to find my p-value. So I draw it out, negative 2.67, that's probably about there on my normal curve. And then I have to ask myself, based on my alternative hypothesis, which direction do I need to shade? This was a less than, so I need to shade in the left tail. So my p-value that I'm looking for is the probability that z is less than negative 2.67. and I look it up on my Z table. So 0.0038, that's my p-value. Everyone get the same thing? So what this tells me is that if my population mean really is 19.5, then the probability of my getting an 18.1077 sample mean, or something less, since that would be more extreme, is only 0.0038. How do you feel about that null hypothesis that my population mean is 19.5? Not very good. So I would say that this is my p-value is smaller than alpha equals my 0.01. And whenever I get a small p-value, I will reject the null hypothesis. So what am I going to tell my boss?
It's a good chance. Time is less than 19.5 minutes.
Okay, so
So there's very strong evidence.
yeah, so we found there's very strong evidence, however you want to word it, very strong evidence that the mean billing time for all, I don't know, accounts or something. Just make sure you put something in that makes me know that you're talking about a population. Is, let's see, so we rejected the null hypothesis. We don't believe that it's 19.5. We believe that it is less than 19.5. So, very strong evidence that the mean billing time is less than 19.5. Okay. Notice here, I don't get to tell my boss that I think it's 18.1 or anything. It's just we found very strong evidence that it is less than 19.5. As far as whether or not that's going to make a practical difference, you would have to actually ask your boss, do we care if we chopped off 1 or 2 days? And then as far as how we interpret our weight of evidence against the null hypothesis, is that statisticians have concluded subjectively that if the p-value for testing the null hypothesis is less than 0.10, then we have some evidence. Less than 0.05, strong. Less than 0.01, very strong. And less than 0.001 is extremely strong. Again, that was just the first people to make it up. Got to decide which words they would use. So it's some evidence that the null hypothesis is not plausible, or strong evidence that the null hypothesis is not plausible. And so once we decide that our null hypothesis is not plausible, that means and that the alternative is true. So usually we will phrase our results in terms of the alternative hypothesis, because that was really what they were interested in. So he was really interested in, is the mean time less than 19.5? And so that's why I said I found very strong evidence that the mean time is less than 19.5. So any questions on that problem from start to finish?
If you were like double check yourself, say, would it be fair to say that if your sample mean, if your sample mean is greater than, like, your sample mean is within your criteria, I guess, for this example, if it's 18 and then if you're looking for anything less than 19.5 without doing all the math, I mean, yeah, you can say it's strong, well, not strong evidence, but you can say that was going to take less than 19.5.
Okay, so
without doing all the math, you just go ahead and...
without doing that. Okay, so this is what I think you're saying. So you're saying we want to know, is mu less than 19.5? So we found x bar equals 18.1077. So you're saying because it was less than that, I automatically think that my population mean is less than 19.5. That's what you're saying, right?
Yeah.
Okay. So what we have to think here is, okay, remember that my X bar changes based from sample to sample, correct? Okay. So if it really was centered at mu equals 19.5, okay, so if it really was 19.5, okay, then could I by chance happen to get an X bar value of 19.6? That's possible, right? It's also possible that I could have gotten like 19.4. Okay, I could have also gotten 18.9. Okay, I might have. Could I possibly get like X bar equals 26? Maybe, but it's probably kind of unlikely. It's going to be kind of far on the tails. And maybe like X bar equals 18.1, X bar equals 17, X bar equals 10, etc. Okay? And so it is possible to get all these sample means. Which sample means are going to be more likely? One's close to my population mean. Okay? Is it still possible to get ones out here? Yes, but not very likely. So what we're doing is we're trying to say, well, how likely was it to get that sample mean if mu really is 19.5? Now, how do you judge how close it is? Okay, so if I just told you, okay, your mean is 19.5, how do you feel about getting a sample mean of 18.1? If I just tell you it's from 19.5 to 18.1, I don't really know, just based on those numbers, if it's going to be close or if it's going to be way out here in the tail. Okay, and so what we have to do is we have to know, well, what is my standard deviation of my X bars? And so the whole point of what we're doing here is that we are saying, okay, this is my difference, and I'm going to divide by the standard deviation to see how many standard deviations I really am away from it. Okay, and then once I do that, I can find the probability of being that far over or more. So it actually turns out the probability of getting 18.1 or less was only 0.0038. Okay, so it was way out there in the tail. We're talking like way out here. Okay. Now, you know that you got that 18.1077, and the probability of getting it, if mu really was 19.5, was only 0.0038. So I believe that I made a mistake, and my population mean was actually somewhere down here. Okay. And so that's really what happens because, so I have a lot of students that try and say that. They're like, well, my sample mean is less than it. Why do I have to do this? Okay. Well, what you're saying is, well, my sample mean, I expect to see some differences, and I'm trying to see, is that difference small enough that it could have just happened by chance, or is it big enough that I really have reason to believe that this number was wrong?
And so we're just proving that number was wrong.
And we're just proving that that number was wrong. Okay. So I'm glad you asked that. I think this was a good way to explain that. Okay. So other questions with it? Okay. We've done hypothesis testing. We've done a couple examples. You're now pros, right?